Thank you very much, Guru. It's a real pleasure to be here. I wanted to start my presentation with two quick stories. First, a word of thanks to Guru. Actually, as I look at the date, December 2018, it was 20 years ago when I first met Guru. He, at the time, was a program director at the National Science Foundation. And he took a chance on a young, insecure, mostly know-nothing faculty member with a career grant, which was sort of the sign of whether you could succeed as a faculty member. He did take that chance. I didn't believe that it was necessarily a good bet, but it worked out for me, and I'm sort of eternally grateful for Guru's guidance over the years. So first, a word of thanks to Guru. Second, based on Guru's presentation, I thought it was very thought-provoking. I wanted to share a story. Actually, I don't think we've ever talked about it before at Google, about how my team came into existence. So it turns out that 10 or 15 years ago, Google's entire network was built on vendor gear, up and down. And we were a young company at the time. But even then, we realized that where we wanted to take the network, we couldn't get there based on the current vendor roadmaps. So we did something along the lines of what Guru outlined. We put out an RFP for what we wanted to deploy at Google. No one responded to the RFP. No joke. We got some side channel feedback, a bit haughty, sometimes even condescending. One, you don't know what you want. Two, it can't be built even if you did know what you want. So with our own, perhaps, hubris, we actually decided that we could just build it ourselves. And that's how actually the network development team was born at Google. So to Guru's point in terms of the puzzle, $1 billion does seem light to me. Google probably runs the world's biggest network. I won't reveal exactly how much we spend on networking, but I would say industry-wide, it's a fair bit. And a different fork in the road would continue to have all of Google infrastructure on vendor gear. Now, I won't lie. I'm glad that we didn't take that path, but I think the opportunity is there for a number of supply chain vendors and product developers to actually do something completely disruptive. So the risk is there, but the risk of not doing it, I would say, is bigger. Okay, so what I wanted to do with this presentation is something a little bit different, something that I've been thinking about a bunch recently. Open source, software-defined networking, why did it win? And actually, when we started, perhaps, and when I certainly started in this field, maybe the motivation was, wow, these boxes that we buy from vendors are expensive, and we can replace them with cheaper boxes. And that was sort of the easy motivation to say, we're going to move from these big, expensive boxes to white boxes, and the network will become cheaper. Actually, in retrospect, that's not why SDN has won. I think that the number one reason in the end that it has won is it allows us to balance availability with velocity. So Google, again, to put it into perspective, we probably every year build a network of the scale and capacity of a 2- or 3-year-old internet. And I mean the entire internet. So in 2018, we'll have built a network, expanded our network to the capacity of a 2015 or 2016 global internet. Just the pace at which we have to move is stunning. Making sure that we can maintain that pace while maintaining the availability of our infrastructure is very challenging. It's probably what we spend most of our time on. And I would argue that without SDN, it would not be possible to do that. So it's not about, hey, can we go buy cheaper boxes to deploy our network? It turns out that our network, while we spend a fair amount of money on it, we don't spend that much money on it. We'd actually be willing to spend, we couldn't buy the network that delivers this capability of growing at this rate while maintaining our availability for any price. And it, as you might imagine, has a huge amount of value for us. So the ability to maintain that balance is probably the number one reason why we had to do SDN and why it's entrenched. To this point, it allows us to simplify reasoning about correctness of our distributed systems. So again, we have thousands, tens of thousands, perhaps hundreds of thousands of switching elements across our network. when we introduce the great and terrible thing about a network is it has global reach and a global blast radius. We have to be able to reason about the introduction of any new network element. And we're introducing new network elements all the time, right? 24/7, every day, 365 days of the year. Somewhere in our network, we are adding a bunch of capacity. And the danger is any one of those operations can bring down a substantial fraction of the network. How do we reason about it and make sure that it's safe? Through verification, through emulation, right? How do we have a essentially copy of our network deployments running in software on the side so that we can test whatever perturbation we're planning on making to the network actually does what we expect. Without SDN, I would once again argue that that's just simply not possible. So then the final bit here is that velocity, what does velocity mean? I should have defined it. How quickly we can move from one version of our network to another, either software or hardware architecture. We need to be able to iterate at Google our software architecture essentially every week. Previously, deploying, and we still deploy some vendor gear, it can easily take 12 to 18 months to qualify a new software release based on vendor gear models. We have to be able to do this every week, right? Every single week across our network, and be able to deploy it globally. Without SDN, this would not be possible. So what I want to emphasize here is that it's not about the fact that the boxes got cheaper. That's maybe a tertiary benefit. We're kind of glad about that. But it's all those other benefits that have really made SDN entrenched for us. So I think in terms of software-driven among 3 dimensions. There's a software-driven data plane. This is the maybe most obvious one, right? How do we move away from big scale-up boxes to disaggregated white boxes? This is probably what gets the most mind share. And I want to emphasize that to me, this is a solved problem, and it's also the least interesting aspect of software-defined networking. Right? So again, actually, the boxes getting cheaper or disaggregated isn't the big win. It's the next 2 steps that are the big win. It's a software-defined control plane. It's allowing us to basically remove from the individual boxes most of the intelligence of the network and put them into a centralized pool of servers that are running software just like any of other services. So our software control infrastructure is similar to how we might build web search or ads or YouTube. Right? It's just another application running on our server infrastructure that happens to control some hardware switches somewhere else. And this is the equivalent of, for example, ONOS that Guru was mentioning earlier. This has been critical to our success, having the software-defined control plane that manages our infrastructure in real time in response to failures and other things. Now, the final bit, I would say that the data plane is in good shape, well understood. The control plane, we're quite happy with. The software-defined management plane, I would say, is a work in progress. And so this, I think, is a huge opportunity across the board, up and down. It's certainly a big challenge for us. How do we continue to grow our network at the pace that it needs to grow at? How do we accelerate it? And how do we maintain our availability requirements in doing so? So think of the control plane as running in real time. Right? It's responding to events, links going up and down, right? Traffic surges coming online, new applications starting up, et cetera. All this we have in reasonable shape. We've talked about it, for example, publicly in the context of our B4 traffic engineering systems, right, where we pick different paths through the network, again in real time, in response to communication patterns. The management plane is about how do we expand our network, how do we drain portions of our network, how do we add capacity, how do we undrain portions of our network. Again, ideally all automated, all under software control, and all verified to be correct. This is a work in progress, and I think that this is perhaps one of the biggest barriers to widespread adoption of some of the ideas that Guru and Andre mentioned early on. All these 3 need to be driven by a robust software engineering framework. You write for test first, you write for verification, and you do emulation-based qualification. Right? You have a shadow, essentially, of your deployment environment up and running, and you know what's going to happen before you actually deploy to production. So going back to when I started off as a young faculty member, what I loved most was performance work. Right? How do I make systems go faster? Really easy to measure. Right? It used to go at X, and now it goes at 1.05X. It's 5% better, and I know that I can claim victory. What I've learned over the years is that actually performance may be the least important aspect of what we do. Right? So how we prioritize infrastructure work at Google and how I think about infrastructure work is actually as follows. It's a pyramid, and the base of the pyramid is availability. Availability, by the way, includes security. Right? If you have an insecure infrastructure, you don't have a reliable infrastructure. So number one is the infrastructure needs to be reliable. People count on our network, both internally and externally. We just literally can't have it down. We actually monitor for availability of our infrastructure and put that as the first thing that all of our engineers work on. Okay. Next level in the pyramid is manageability and capacity delivery. We have to be able to run our infrastructure, just sort of day to day, and a huge part of that is driven by what I mentioned to you before, capacity delivery. We're expanding our network all the time, and it's really hard, actually. Right? The faster we can expand it, the better we do overall. In other words, we need to have predictable delivery of our infrastructure, of our network infrastructure, where and when we need it. That's got to be really easy and smooth. Once we have that, we can go to velocity. How often, how frequently can we, subject to availability and manageability, upgrade the functionality of our infrastructure? So the beautiful thing about software-defined is we don't have to wait for new hardware capability to introduce new features. So a lot of conversations I hear from colleagues in the rest of industry is, hey, we have to wait for this new chipset to support, I don't know, this new GRE and CAP functionality or another level of MPLS or VXLAN, this, that, or the other. At Google, that tends not to be a conversation piece. Right? We're not waiting for the next hardware chip that can do some specific piece of functionality. We do push almost all of that to software. And ideally, we're pushing those updates, again, weekly. We're qualifying them weekly so that we don't have to worry about, okay, it's going to take us 18 months or 24 months to get some new feature out there. Once we have velocity, we think about stranding. How do we make sure that we have the right capacity in the right places at the right time so that we don't turn up too early or worse, too late? Finally, once we have all these basics in place, we can get to the fun part. Right? Or the fun part that I still hold is the fun part, and that's performance. How do we make the network really, really fast? But we have to start at the bottom of the pyramid here and get our base really solid. Highest levels of availability, highest levels of security. And the network, of course, is key to that. Right? Fortunately or unfortunately, our most spectacular failures tend to center around the network. It's a big responsibility. So just to emphasize, right, an insecure infrastructure is not an available infrastructure. So I've said this before, I'll repeat it. Not only are we always delivering new capacity, we are always under attack. Right? Google is constantly under attack from one place to another, 24/7. The only question is, what is the magnitude of the attack? It's not whether we're under attack, it's how bad is the attack currently. Okay. So the stability of our infrastructure is more important than its efficiency. What we do, actually, is we catalog every failure that we have. Certainly the big ones, but also the smaller ones. So one of the things that this has allowed us to do is essentially be able to can categorize every minute for every one of our networks as either good or bad. We have a high bar for a good minute. In other words, externally, no one might notice. We might still be unhappy with the behavior of our network in a particular minute in a particular location. We catalog every bad minute at Google, and we root cause and attribute it to something. We then have buckets that say, here are the root causes for all of the bad minutes in our network. This leads to a set of features. Of course, we prioritize the implementation of those features based on the magnitude of impact that they've had historically. We do find that the past failures are a great predictor of future failures, and that there's strong correlation there. This then goes back to the point of velocity. We might have 10, 20, 30, 40 features at any point in time that need to be developed and deployed to the network globally in order to stem those bad minutes that we've seen. Okay. If we have to wait 18 months to get a new feature out, we're in big trouble. If we can get them out on a weekly basis, we can continue to keep up with the pace of our innovation. And new sources of problems come up all the time. Our network's changing in new and interesting and exciting ways all the time. So we're always playing catch up. But if we're playing catch up with a week or two lag, we're in much better shape than, essentially, it's not even possible to play catch up if your lag is 18 to 24 months. Right? Not something that you could contemplate doing. What you then do is get conservative. If you have an 18 to 24 month lag, you actually say, I'm not going to deploy new functionality. That's too scary. And it would be too scary if you put availability at the base of your pyramid, which of course we believe you should. So then the twin part of availability is velocity, right? And this is why SDN is so critical. So if you remember one thing here, from my perspective, it's SDN allows you to balance availability and velocity. And my version of the yin and the yang, I don't have the beautiful yin and the yang picture like Guru does, is that the two of these go hand in hand. One enables the other in a virtuous cycle. So it's velocity here, lots of different definitions, is the speed of iteration. So how quickly can you decide that your new feature, your new piece of functionality is correct for your global deployment infrastructure? And you now have hardware that might be 6, 7, we're not quite to 50-year-old hardware deployments, 10 years old. Maybe we will have that privilege at some point. But highly heterogeneous. You have a new feature, you've written it, developers say it looks safe, developers are highly optimistic. Is it going to work? Right? How do you have the highest level of confidence that it does? Such that, say 99% of the time when you do a software update, it just goes out across your entire global network with no issues. Right? And that's what velocity is all about. Okay, I want to shift gears a little bit here to now come back to another point and argue about why networking is actually even going to be more important in the 10 years ahead than in the past 10 years. And that's because of some of the macro trends that we're seeing, that I'm seeing in neighboring domains, compute and storage. So what we've seen is that loosely coupled distributed computing has been the rule for 30 years. So essentially what I mean here is that if I'm going to have a computation that runs across multiple servers, even as a developer, I want to have as much autonomy on a per server basis as possible. I design my system not to rely on another server, because that couples them, it introduces bugs, it introduces huge slowdowns. From the perspective of a developer, a remote server is something to avoid. It's a thing that you have to take on because you have to take it on. And that's been okay because individual servers up until recently have gotten twice as fast every 12 months, every 18 months, maybe now every 24 months. Right, so you could afford to just wait for your code to get faster. You could wait to have more and more capability on individual servers rather than have to count on the capability of some other server in your distributed computing pool. Those days are over. I'll show a couple of graphs here. What this means is that actually the network is going to have to play an even more important role in building next generation services, because the only way for us to build more capability into our services is to leverage the processing power and the storage of remote servers. So let's look at a couple of graphs here. Here is a look back at processor performance over 40 years. So what you have here on the x-axis is time. 40 years have passed. On the y-axis, we have normalized CPU performance, with 1.0 being an academic's favorite computer, the VAX 11780. Right? Some of you might remember that. What you can see is just massive performance improvements. And you'll notice that the y-axis is on an exponential, right? The straight line in the green showed just incredible performance improvements over a 20-year period, right? Doubling in performance every year and a half. Over the past 5 years or so, that's crawled to a halt. I think essentially what we can expect now in terms of processor performance is a couple of % a year, especially when normalized to cost. You might be able to get more performance out of a single chip, but you're going to have to pay a lot more for it. This is all normalized to cost as well. So what this means is that if you want to build a more capable service, you no longer have the luxury, the beautiful luxury, of being able to wait for a faster server to come along to absorb the new functionality that you want to deploy. You have to build more tightly coupled systems. So corresponding graph, that's somewhat scary for us. Data is growing faster than compute, and substantially faster. So once again, an exponential on the y-axis, a lesser time period, about 10 years. What the big X's show here is the number of hours per minute of video uploaded to YouTube. And basically, human-generated video content, this is to Andre's point of how much of the internet is about video, is just growing at an exponential rate. The thing that we found again and again, though, is that computers generate data at a much higher rate than humans generate data, actually. And so what I'm not showing you here is the amount of data that our applications are generating over that same 10-year period. The hint is it's even more. So the rate of data growth from computers is enormous, from humans is enormous. This is going to continue to accelerate with IoT. Right now, if you have every camera in your house that's connected to the quote-unquote cloud, this is just going to accelerate. The blue dots is what's happening with spec-int compute. So we're continuing to generate huge amounts of data on an exponential that has to be processed one place or another. Our compute infrastructure isn't able to keep up at this point. So that means that either we're going to have to pay a lot more to process that data, normalized, or we're going to have to come up with novel ways to do that data processing. Taking some examples from Google, I think it's, sometimes we take it for granted, but when you make a single request to a web service, right, when you pull up a map on Google Maps, the number of different services, back-end services that have to be coordinated together to produce the HTML that makes up your web response is just stunning. Right? I mean, the sort of old days of what a web request and response looks like are long gone. We have dozens, perhaps hundreds of individual services, each going through huge amounts of data in real time, right? Let's say 100 milliseconds or less, to produce that page for you, personalized to that exact moment that you made the request and exact, potentially, real-time conditions of the world, right? What's the traffic look like right now? Right? Which stores are open right now? Which stores wants to generate an advertisement for you right now? Right? Et cetera, et cetera, et cetera. So the amount of data, the amount of compute that's being done millions of times per second and growing is just stunning. And the other part is our application developers wish they could be doing a lot more for every single one of these requests. They're limited by, well, I'm biased, but they're limited by the network. They're limited by their compute budget, and they're limited by the amount of data that they can access in that 100 milliseconds, and that they can join together in that 100 milliseconds. We need a better network that we can update more frequently in order to be able to meet their needs and hence be able to deliver richer services to users across the planet. Okay, I'm going to skip this for time. A couple more examples. This was when I was in graduate school, a bit of science fiction. But you can now use your camera to be looking at the world through your lens and getting real-time information on what you're seeing. Certainly, you can recognize text and translate it potentially to your language in real time, but you can know exactly what you're looking at and be getting feedback. So just imagine the amount of data that's being processed in real time with sort of 100 millisecond response times to be able to do this. We lost something in making PDF, but what you can now, this is the audience participation part, imagine that you are on a bumpy 4x4 vehicle and the video on the left is moving up and down, right, as you're taking it. And on the right, there's a perfectly still playback of that exact same video being generated in real time based on huge amounts of data processing. So this is actually working now, essentially. Smart reply. 10 years ago, this was actually an internal April Fool's Day joke at Google, that we would be able to look at a message and come up with a good response for it. 6 years later, we were able to launch a real product. And a year after that, more than 10% of mobile inbox replies are using it. So again, in real time, we can look at an email message, propose 3 replies, and more than 10% of the time, people pick one of those 3 replies as being equal to or better than what they might have typed themselves. So the network, I would say, is at a crossroads. I think that ONF and the open network community is at a critical point. Actually, I think that the opportunity relative to when we put out our RFP 10 or 15 years ago is much larger. And the role that networking is going to play in what computing looks like is going to grow. So people shouldn't be viewing this as cannibalizing existing sales. I think people should be viewing this as the sales for networking actually needs to grow. How much people are willing to spend on networking, given the capabilities that it could give them, will be larger, should be larger. So why are we at this crossroads? What we're seeing is it's the end of Moore's Law. Right? Your servers aren't going to get any faster. This is actually, I mean, it's a scary fact, and it's one that's driven Silicon Valley for 40 years. We're going to have to do something about it. I know we will, right? I mean, the whole community is about innovation. Data is continuing to grow, though, at astounding rates. And what this means is that our computing demand is continuing to grow at astounding rates. So the network that's going to enable this, there's 2 paths forward. It's a whole other talk. But path number 1 is we're going to need accelerators, special purpose hardware. And we're going to need more tightly coupled compute, general purpose compute. The network and the network fabric is going to play a critical role in tying both of those things together. Right? Now, again, separate talk, but how you plug in an accelerator into a compute pool is going to involve a lot of networking. And then how you bring the servers together to cooperate on these hundreds, thousands of individual services that are delivering rich responses to users across the planet in real time, the network's going to play a really important role there. So bringing this back to Google, just showing a couple of pictures of what our infrastructure looks like. This is a bit dated now, but basically what you can see is approximately 100 blue dots across the world. These are our points of presence. This is where we peer with our partner ISPs to deliver our network connectivity. This is our public network, including a private submarine network of fiber that connects the world together. It's a bit faint, but you also see a larger number of yellow circles. These are our deployments of servers in our partner ISPs networks as well. So what we found is that we can deliver content more efficiently, more reliably from our partner ISPs in many cases than, of course, from our own network, and we take advantage of that. And here is an alternate view, a bit more up to date, more under sort of subsea cables, more points of presence, and highlighting the Google Cloud Platform's presence at many, many more regions across the world as we expand to different geographies. So 2 takeaways from this. One is that Google's share of the global internet, as depicted here, actually is growing over time. So in other words, the internet is growing at an incredible pace. Google's fraction of those bytes is increasing even faster over time. That's part 1. We actually run 2 networks. This is our public network. Connecting our data centers together is our private network. Our private network is actually, at this point, substantially larger than our public network and growing faster. So while our public network is big and probably one of the biggest on the internet, it is our private network, right? So this, once again, goes to the point of computer-to-computer communication dominates computer-to-human communication. It's bigger, it's growing faster. And without going into the details, all of our infrastructure at Google now is essentially SDN. So we have 4 pillars here. We have our private wide area network, B4. We have a software-defined packet processing infrastructure, similar to the infrastructure that Guru described, USPS, that underlies much of our end host delivery of data across the network. We have our Jupyter data center network, and we have our Espresso peering infrastructure. All of it SDN based, all of it being expanded and delivering new capabilities using the SDN principles. I will stop here. without going into the details of some of the subcomponents and take some questions. Yeah, great.
Can we get a microphone here?
Amin, thank you for your talk and very interesting. It seems like you, if I were to simply put it, you're saying that the compute is now becoming the data center, right? Your computer is becoming the data center. Do you see silicon photonics as the most critical advancement enabling that? And if that's the case, where do you think the value of, or where the value of the network shift? Does it shift towards the optical component layer on the silicon photonics level? Is it still in the networking processing there? Can you elaborate a little bit more there?
We're excited about silicon photonics. I wouldn't say that it's the most critical portion of our network infrastructure. I think that, again, speaking frankly and directly, it's still on the cusp of being critical. It will be critical in the years ahead. I would say that in terms of the shift, silicon photonics side is really about driving down some of the costs required to bringing these servers closer and closer together. I would say actually the bigger issue that we're facing is the software overheads rather than the costs. In other words, we, at this point in time, are able to deliver huge amounts of bandwidth between our servers, and we do. Where we're working hard is reducing the overhead, the software overhead, essentially, of opening up those bits per second.
Any other questions? Oh.
Thank you very much for the enlightening talk. What amazes me is you are saying that we are moving more towards proprietary stuff rather than based on the requirement on the networking side. Compute being now the dinosaurs, we have to extract value out of networking. Is that correct, what I hear from you?
I want to make sure I understand the question. Are you saying we're moving more toward proprietary solutions?
That's what you indicated.
So I would say it's not that we're moving more toward proprietary solutions. What we are hoping, so in other words, if I were to look at the stack that Google presented, Guru presented early on, we have the exact same stack. And why we're a huge supporter of ONF and the open source movement is that we want to and support an open source infrastructure that we could leverage. Now, it is the case that we have our own stack internally at Google. We're working hard to get basically the external side of things to the point where it's one and the same, where our internal infrastructure can be the same as our external infrastructure. You're seeing the first signs of that with the Stratum effort, which I think it's fair to say Google is maybe the lead or certainly one of the leads on, and we're hoping that that changes. So it's not so much about us wanting to go after proprietary solutions. We want to actually seed the architectures. You're seeing some of that here. What we need, I think, is that jumping in with 2 feet aspect of it that has been missing so far in being able to leverage some of these things for internal Google use or some of our other partners.
So, I mean, if I may ask, we get to interact in other contexts as well, but I thought I will just ask this in this context. That is, this idea of FDN about the velocity and the availability. So we at ONF have not done as much as a community to build the availability part of it as much. Especially, there is a lot of good research that has came out of Stanford and Google and all of that about how FDN enables verification and all of that, because you have the logically centralized control plane, the global visibility, and on top of that you can build all of that. So you think maybe ONF should be focusing more of its resources and thing on building those verification and all those tool chain for open source? Or we haven't had that conversation, so what would be your recommendation?
I would say so, and I think that's, I'll again maybe use a public analogy where when VMware wound up deploying and selling NSX as a product, right? It was a SDN stack, but what was the most appealing version of it from the perspective of consumers? It was about microsegmentation and it was about security, right? So it's a huge product, lots of revenue, I would say predicated on availability. So I think that the point that I was trying to make, maybe obliquely, is that many people would spend a lot of money on having a high velocity, highly available network infrastructure. And it's not that actually they want to spend less money on the network by getting to white boxes. That seems like it's an initial hook that's easy to understand. But the bigger opportunity is my network, I can't move fast enough with it. I mean, ask any operator, and most of them will say publicly, and the others will say privately, I can't move fast enough on our network. And it's not nearly as reliable as I want. I'm getting too many calls on Friday nights, right? Too many calls on the weekends with some portion of my network blowing up.
Yeah.
I shouldn't say this, but I sleep well at night.
So one last thing, I think a lot of industry has moved to white boxes with still the distributed control plane and not really gotten to the SDN based control plane. So you think this is too incremental and they would have?
I think they're not using SDN.
Okay.
Yeah.
Anyway, I think so maybe I'll stop. Any other questions, or maybe last question before we let Amin go? You don't get an opportunity to ask questions to Amin, so maybe last question.
So I have a question on the declining rate of gains in processor speeds and efficiencies, correct? But what we have seen in the code side, that programmers have gone up to the abstraction layers to higher level languages, and lot of, like Google uses a lot of RPCs, correct? So it brings in inefficiencies. So what is your thought on how to make it, like how to address this challenge of conflicting interests?
It's a great point, and I think that actually there's going to be some culture lag. I think that absolutely human productivity is critical, and that's probably one of the top things to optimize for. I would say, however, though, that the ability to absorb inefficiency has been driven by the fact that single server efficiency has grown so rapidly. And I think that it also depends on where you're looking in the stack. In other words, if you're delivering sort of user interfaces, you probably don't want to be writing assembler code. At the same time, if there is something that's absolutely critical, like your RPC package, perhaps your messaging package, and that is used by thousands, tens of thousands, hundreds of thousands of developers, maybe it makes sense to have a core team of 10, maybe the top efficiency core team of 10 in the world or in your company focused on looking at L1 cache locality for that particular line of code. Maybe hand tune some of the assembler there. I think certainly we see that at Google, that there are different programming environments, languages, and tools that are appropriate for different jobs. For the lowest levels of our networking stack, we worry about every branch prediction and every branch miss. We're looking at, again, I won't share the numbers here, but I'm quite comfortable with the level of efficiency that we're able to deliver relative to what's possible in the underlying hardware.
Okay, I think with that, really? Okay, one last one, Amin.
Hi, I mean, I didn't want to lose the opportunity to ask question to you. So, sorry for this last question. So, my question is the SDN only right thing to go to future with, or a proper balance? So, SDN talks about taking the control plane out of the networking devices completely. Or do you see that a proper balance of control plane, some functionality in the networking devices, and only which actually makes sense to be moved out of the networking device should be moved out, not the way everybody's thinking right now?
You're absolutely right. I think that it doesn't make any sense to move everything out of the individual boxes. I think that what we're saying here is that you want to have the right functionality. It's not about a religion. It's not about saying everything must be centralized, everything must be fully distributed. And even centralized doesn't mean fully centralized necessarily. It's not like Google's global network has one single server somewhere in one place that controls the entire infrastructure. It's replicated, it's hierarchical. What's the leaves of the hierarchy? The switches, the servers. So would you have some functionality on the switches and the servers? Absolutely. And do we? Absolutely. The question is, do you want to have your fairly complicated distributed coordination having to run at the leaves? I'd say in rare cases, very rare cases. But if you can handle to me this is an instance of the end-to-end argument. If you can handle some events entirely locally, why make it distributed? That would be silly, right? And do so. So that's the reasoning that we use. If you can handle it as locally as possible, but no more locally, if that makes sense.